Hello everyone, I am Nikhil Suryawanshi, currently working as a principal software engineer in the United States of America. I have pursued a double master's from the United States of America in computer science and in information technology management. In the recent years, I have extensively been involved in research in the application of AI and machine learning in various domains, such as healthcare. My recent research enhancing breast cancer diagnosis through clustering, a study of k-means, agglomerative, and Gaussian mixture model is in the healthcare domain, which also is the topic of today's presentation. In the recent years, there has been an enormous development in the healthcare, where technology has played a huge role in diagnosis and cure of the disease. Breast cancer is one of the rapidly growing and commonly seen diseases in female, with a ratio of 1 in every 8 women and about 13% of lifetime risk of developing it. Hence, there is a need to develop the methodology for accurate and early diagnosis of the disease. In my research, I have tried to address these issues with the help of machine learning and clustering algorithms. Abstract. In the evolving landscape of the medical data analysis, clustering techniques play a pivotal role, particularly in deciphering intricate patterns within datasets such as those linked to cancer diagnosis. With the continuous expansion and increasing complexity of the healthcare data, there is a growing demand of effective clustering algorithm capable of extracting significant insight. Current, current trends underscores the necessity of carefully selecting the most appropriate clustering methods to improve both the accuracy and inter interpretability of analytical results. In this paper, we conduct a comprehensive comparison of three prominent clustering algorithms, that is k-means clustering, agglomerative clustering, and Gaussian mixture model, when applied to breast cancer dataset comprising features from fine needle aspirants (FNA) of a breast masses. Following a thorough pre-processing and scaling of the features, we assess the performance of these clustering techniques using the Schulhut score, Kalinske-Harbers score, and Davis-Baldwin score. The findings reveal that k-means provides superior cluster separation and clarity relative to other algorithms. This research emphasizes the critical role of the algorithm selection based on the specific data set attributes and evaluation metrics, aiming to enhance the accuracy of clustering outcome in the breast cancer classification. In the recent digital age, technological advancements have led to an unprecedented surge in the data generation across various devices and platforms. That has given rise to what it is commonly known as a big data. This term encapsulates the vast quantity of information produced at an accelerated pace and in diverse formats. Traditional data processing and analysis methods often struggle to manage and extract the value from this overwhelming data, and as a result, advanced machine learning models have become essential for effective clustering and deriving insights from such a complex data. A clustering is a core task in unsupervised machine learning, which involves grouping of data points into cluster based on inherent similarities. In the context of big data, clustering is crucial for uncovering hidden patterns, detecting anomalies, and supporting data-driven decision-making processes. However, the high dimensionality, variety, and sheer size of a big data present significant challenges to conventional clustering algorithms. This necessitates the development of more sophisticated machine learning model that can handle the complexity and scale of these datasets. In the medical field, particularly in the analysis of breast cancer data, clustering techniques have proven invaluable. They are so important. Breast cancer remains one of the most prevalent and life-threatening diseases worldwide, compelling yearly and accurate diagnosis. Clustering algorithms can assist in categorizing patients based on similarities, diagnostic features, identifying subtypes of the diseases, and even predicting treatment outcome. By effective grouping of data points, clustering aids in the personalization of treatment plans, ensuring that patients receive the most appropriate care based on their specific cancer profiles. Recent progresses in the machine learning has led to the creation of cutting-edge models tailored specifically for clustering within the realm of the big data. This model incorporates advanced techniques such as deep learning, ensemble methods, and hybrid approaches to overcome the limitations of traditional clustering algorithms. The rise of the distributed computing frameworks like Apache Hadoop and Apache Spark has further transformed big data processing, providing the computational power necessary for advanced machine learning models. Our research objectives. The objective of this research is to conduct a comprehensive comparison of three prominent clustering algorithms, that is K-means clustering, agglomerative clustering, and Gaussian mixture model, by applying them to the breast cancer dataset comprising features from the fine needle aspirates of the breast masses. Another aspect is to highlight the importance of selecting the appropriate clustering algorithms based on the specific needs of the dataset and the desired outcomes to enhance the accuracy of clustering outcomes in the breast cancer. We have proposed a system that could provide us with a better output and a solution for perfect analysis of the breast cancer data. The architecture, as shown in the figure, of a clustering analysis system consists of several key components that work together to pre-process the dataset, applying clustering algorithms, and evaluate their performance. The main stage of the architecture are as first data loading and pre-processing. This step, where the process begins within loading the breast cancer dataset, which contains features extracted from digitalized image of a fine needle aspirants of a breast masses. This feature describes the characteristic of cell nuclei that is present in the image, providing essential data for clustering. To ensure the data integrity, any rows with the missing values are removed during this process. Second step is feature encoding. Since the dataset may include categorical value variables, these are identified and transformed into numerical values using label encoding. This step ensures that the machine learning algorithm can effectively process all the features by converting categorical data into numerical format. Then third step is feature selection and scaling. Once the data is encoded, relevant features are selected for clustering, typically excluding any target or a label columns. These selected features are then standardized using feature scaling techniques such as standardization. This step is crucial as it normalizes the data, ensuring that each feature contributes equally to the clustering process. Then fourth stage is dimensionality reduction. This is optional but better to perform. To facilitate visualization and reduce computational complexity, principal component analysis, that is known as PCA, is applied to the dataset. This PCA reduces the dimensionality of the feature space to two dimension, making it easier to visualize the clustering results while retaining as much variance as possible from the original data. Now comes to the major portion of where we apply clustering algorithms. The core of this analysis involves applying three different clustering algorithms. As we know, k-means clustering, agglomerative clustering, and Gaussian mixture model. Each clustering algorithm processing is consisting of multiple processing steps. So we'll start with the k-means clustering. First step is initialization. K-means starts by randomly selecting a predefined number of centroids. Then assignment. Each data point is assigned to the nearest centroid based on the Euclidean distance, forming initial clusters. Then update stage, where the algorithm recalculates the centroids by computing the mean of all data points within each cluster. And last stage is iteration. The task and the upgrade steps are repeated until these centroids no longer changes significantly or the highest numbers of iteration is reached. Similarly, for another clustering, that is agglomerative clustering, there are three stages. First one is initialization. This hierarchical clustering method treats each data point as an individual cluster. Second step is merging. It repeatedly merges the two closest clusters based on the distance metric, typically using Ward's linkage method to minimize the variance within clusters. And the last is a competition. The process continues until the desired number of clusters is achieved. Similarly, in the third clustering method, that is Gaussian mixture model, we have three stages, that is initialization, expectation minimization, and iteration. In initialization stage, the concept is GMM accepts that the information is reduced from a blend of few Gaussian dimensions with the obscure parameter. In second stage, where expectations minimization, the EM algorithm is used to find the maximum likelihood estimate of the parameter. In the exception step, the algorithm calculates the probability of each data point that is belonging to the each Gaussian component. In iteration, this process is iterated until the convergence resulting in probabilistic clustering. Dataset. The dataset we have used is sourced from Social Good Women Coders Bootcamp organized by Artificial Intelligence for Development in collaboration with UNDP Nepal. It was downloaded from the website known as Kaggle and comprises features derived from digitized images of a fine needle aspirants FNA of a breast masses. This feature captures various characteristics of the cell nuclei present in the images, which are essential for diagnosis of the breast cancer. Then methodologies used in this process to calculate the clustering and achieve the results. So there are a couple of algorithms applied here to evaluate the performance of our proposed model, which applies to the k-means clustering, agglomerative clustering, and Gaussian mixture model algorithms to the breast cancer dataset. We utilize three matrices, that is Silhouette score, Kalinske and Herbaz score, Davis and Baldwin score. In the first one, where Silhouette score, we measure how well each data point aligns with its cluster compared to other cluster. A higher score ranging from -1 to 1 indicates better separation between clusters. You can see this in the image below. Then the second method is Kalinske-Harbach score, where it assesses the ratio of the between cluster to within clusters dispersion. A higher score signifies more distinct and well-defined clusters. And in third, Davis-Baldwin score, it evaluates average similarity between clusters with lower score indicating better clustering. All these matrices have their own formulas through which we have been able to calculate the clustering and have mapped it into graphical format. Now the results. The clustering performance of the k-means clustering, agglomerative clustering, and the Gaussian mixture model algorithms on the breast cancer dataset was evaluated using Seelhorst score, the Kalinske-Haber score, and the Davis-Baldwin score. Now this chart shows that the k-means algorithm is well scattered and has good values and is on the top of the list. If we have to see the comparison, the Seelhorst score indicates how well separated the clusters are, with the higher values signifying better clusters, and the figure below shows the analysis of the Seelhorst score and the Davis-Baldwin score. The k-mean algorithm achieved Seelhorst score of 0.4711, slightly higher than the agglomerative clustering, which is 0.4631, and the GMM, which is 0.4703, where it clearly suggests that the k-means provide the most distinct clustering among the three algorithms. In the Kalinske-Haber score, the k-mean algorithm achieved the highest score of 523.4, followed by agglomerative, which has 494.13, and followed by GMM, which is 429.35. In this metric as well, the k-means is on the top. And in the Davis-Baldwin score, the k-mean achieved 0.9263, which is lower than agglomerative clustering, which is 0.9750, and GMM is 1.0203. The result suggests that the k-mean clusters are more compact and distinct compared to those produced by other two algorithms. Hence, our conclusion clearly says that k-means has achieved the superior performance in the majority of the evaluation of matrix. So in this paper, we have proposed the comparative analysis of k-means algorithm, agglomerative clustering, and Gaussian mixture model, which has applied to the breast cancer datasets derived from the fine needle aspirants of our breast masses. As per our findings, the k-means is on the top with the superior performance. This suggests that the k-mean is more effective choice for a dataset where clear and distinct cluster boundaries are crucial, while agglomerative clustering and GMM also contribute valuable insight. Their clustering quality was slightly less favorable compared to k-means, especially concerning cluster distinctiveness. The results highlight the importance of the selecting the appropriate clustering algorithm based on the specific needs of the dataset and the desired outcomes. Now the recommendations for the future studies. In the future research, we should explore various aspects of enhanced clustering performance, such as adjusting the number of clusters, incorporating additional features, or applying advanced and hybrid clustering techniques. By addressing these areas, researchers can refine breast cancer classification methods and improve data-driven diagnostic accuracy. Thank you very much.